So you're looking at exponential functions, growth and decay. Remember, your parent function basically is a function of y in respect to x being the independent variable. This is the piece that changes. This is your constant. But you do have some instances where this is taking effect to let's say an a here, an additional variable. And I'll show you that with this here. This is a cool situation. I don't know if when a seed buds, it usually has 12 cells. I just use the smaller number. But this rate of cells doubling each hour, is in some cases true, and it's pretty neat to look at. But what you're looking at is, okay, what is going to be my output, my y? What is going to be my amount of cells if a certain amount of cells I started with grows or decays at a certain rate over a certain amount of time? This is usually your time. This is usually your rate as far as growth and decay, and then this is usually what, almost you could think of this like a y-intercept. It's what you're starting with. It's the piece that it's having an effect on. So when I make my function here, I say, okay, I started with 12 cells. It's doubling as a growth. That's a growth. It's doubling each hour. But basically, if I'm looking to graph this and see how many hours, that's where my variable is. All right, because I don't know how many hours I'm talking about. A 1 hour, yeah, okay, it becomes 24, it doubled. But at 2 hours, 3 hours, because this is the part that's becoming exponential. This is the part that is increasing at an increasing rate. So when I try to graph this with my TI-84 tool here, simply just putting in this as a function. Now, you're not putting a number like 1 for the hour. This is the independent variable. This is what's changing. So you're using your variable button right here, and you're putting in an x. And then you're graphing this here. Now, sometimes your dimensions will fall off here. So you want to look at your zoom, and then maybe go to a zoom standard. Invalid dimensions given me, so see what I did there, incorrect. Something happened with my plots. Okay, so if this happens on your calculator, like it starts to malfunction, you can go to second, quit, second, memory, what I'll do, and I'll reset, and I'll actually reset to all my defaults, because something happened when we were messing around with the plots. And then I could go back to here and then graph, and then it'll give me my graph again. So that's a good little hint if your calculator's not working appropriately. You can see that nothing's taken place on this window here. So I might need to zoom out. So you can go to your zoom out function. You have to hit enter, and when you hit enter, each time you hit enter, it'll actually zoom out, and then you're waiting for the wheel to come up. I don't know what the problem is here. Let me try this again. I'll reset everything. Okay. 12.2. Use my variable graph. Okay, so here we have some of our graph here. I want to zoom out a bit. And you see a couple things. Okay, you see it's crossing over here the y-axis. And if I want to see what's taking place on the graph, I can use this trace button and kind of see what's happening as the graph goes along. One point I see here is the x is 0 and the y is 12. So if I'm looking at my graph here, okay, I see I have a point I can graph as 12. Okay, a couple other points maybe I want to look at. I have a -3 and a 1.5. So maybe I want to go to -3 and a 1.5. Yeah. When I started, Yeah, I was zoomed in. So if you want to go back to your original graph, this is what we had originally, and you can see it's intersecting right up above here at about 12. So what I did was I zoomed out, and I got a better visual of what it's doing, right? And you know, when we're graphing the function, I'm just basically looking for a sketch of some sort. Um, you have the graph on your calculator, and we're seeing, okay, it's starting at 0 time, it's starting at 12 cells, or when the seed buds start at 12 cells. And you can see this graph here that's kind of going up. It's increasing at an increasing rate here. Okay, you can see this graph going up here. Now, some things we want to look at is what's happening you can see how quickly it's going up. After about 2 hours, we're about 64 cells. 3 hours, you're about 98. And the question I asked you is use the graph to predict the amount of cells after 1 day. Okay? Now, 1 day in hours is about 24 hours. So what I could do is just trace this graph until my x value here, is about 24. And I have a pretty big number here. We could say at about, and now you could use your x value here and say at about 24.24 hours, you have about 238 million, right? This is pretty good information. You could also use your table and go to exactly where 24 hours is here. And you see it says, you see at where x is 24, it's saying 2.01E8. Now this is kind of like scientific notation. What that's saying is it's taking the 2.01 and it's moving it 8 times. 1, 2, 3, 4, 5, 6, 7, 8. So we could just fill this in with zeros here and say, okay, I have about 201 and 1, 2, 3, 4, 5, 6 zeros. And I have about 201 million cells here. Okay. Now another thing you can take a look while you're doing this, which was shown by a student, is second calc, right? And you have your value. You can calculate when x is 24, and they'll show you actually the full number here, right, on the graph, because on the table it's showing you the 201 million. When you use your second calc and you find the value exactly what you have at 24, it gives you a full number of 201, 326, 592. So we have a pretty accurate number here at 24. I mean, it doesn't get any more accurate than this. And we're able to do that using the calc button, which is above the trace button on your calculator here. Yeah, I put it in, second, calc, my 0, and I can look, okay, what happens at 20 hours? And that gives me my value here, it's about 1,258,000. This right here, the window you can determine, so this is my window's currently showing my x-axis at -40 and 40. So basically my window is showing that this is -40 and this is 40. This is 40 and this is -40. That's what's being shown on my calculator right there. So if I don't want to pay attention to some of the x values here, maybe I want to change this to a -10. Okay, maybe because we're not really looking at negative time, so maybe I just want to change my window to be at -5, like right here. I would just change my window to -5 and graph that, and you can see my window's changed. And then it seems like a lot of this too I don't really need, so maybe I want to change my window to be at, we're looking at 24 hours, so let's make it 30. And then we see our y min is like our y max is a pretty big number. It doesn't go below 0, so we'll just say -5 here. And maybe we'll use like 1,000, right? And you could see how I'm changing my window and how to look at the graph in different ways when I'm doing that. The first problem we talked about was growth. This one is, in a sense, decay. It's weird to talk about a ball bouncing as far as decay. But again, you have your y, you have your possible a, which is, some sort of value you start with, a constant growth or decay, and your variable, which is like how many times is this happening. So you start at 30 feet. It's decaying at 3/5 of its height. So you can write this as 3/5 to the x, or you can write this, which is what I would do, as 0.6 to the x. Okay. Now when I'm graphing this function, all of the same things kind of take place here, where, okay, I'm going to go 30, 0.6, and then, mistake I made there is I did not make it an exponent. So let's climb this up, climbing up the ladder. You can see how my window's a little off here. It's still working. Okay, so what I like to do is I like to go to second. I like to go to my, oh no, I don't need second there. I just go to zoom, and I go to 6, my zoom standard, which kind of brings me back to my original graph there. And I see some pieces here. I'd like to see where this kind of starts at the y-axis. So maybe, since the height is 30 feet, maybe I'll change my window of my y max to be about 40. And I have a really solid graph here. And I could trace, and it shows me right away, okay, my graph is at 0 and 30. A couple things I like to do with trace too is, so I'm starting at 0 and 30. Here's my 30. I could plot some points so I could sketch my graph. Here at 1, it's about 17. So let's say this is 30. Let's say this is 20. At 1, it's about 17. I could also use my table to kind of plot some points. You can even see at 1 bounce, it's 18 here. So actually, right here at 1 bounce, it's 18. You really only need to plot a few points to get kind of at 3, we're at 6.5, right? And you have the graph here too, so you can sketch it, you can trace it, kind of, where is it approaching your x or your y being 0? So at about 7, let's see, does it go about 9? It's almost at 0 at 10. So let's say you go to 10, and then you sketch your graph, and you can see it's getting really close to 10 here, right? We're sketching our graph. Now some things we want to look at, and you got to be careful because they do this on the SAT. They gave you originally the question in feet. They gave it to you in feet, but here you see I put it in italics and bold. Okay, we're looking at inches. So a lot of you guys traced and you looked where x was, or y was 6. So if you see y is 6 at about 3.1 bounces, right? Even if we look at our table here. Between 3 and 4 bounces, it goes from 6 feet, but that's not what we're looking for. We're looking at 6 inches, which is technically 0.5 feet. So I'm actually looking at where my feet is 0.5, right? And if you see at 8, it's 5.03. I'm sorry, it's 0.5039, and at 9. It's 0.3023. So after about how many bounces, you could say in between about 8 bounces, or in between 8 to 9 bounces is when the rebound will be less than 6 inches.